All right, recorded is ready, rolling. You guys have got some data for the first half of the lab. So let me go ahead and walk you guys through maybe what an example could look like. Right? So some weights, say 50-gram weight. Oh, by weigh like a half a Newton. If you have 100 grams, probably weigh pretty close to 1 Newton. 200 grams, right? It's like I picked this up with the spring scale, right? 200 grams. What's that? Oh, well, it's like 2 newtons. 2 newtons treated, right? So there's my 2 Newton weight, right? There's a 5 Newton weight. There was a 10 Newton weight, right? Maybe use some other ones. Right? So here's an example. Okay. Then how much force to pull at constant velocity across the surface? Right? So if I'm pulling it constant velocity, something like that. Right. So for the 1 Newton weight, maybe this was like 0.3 newtons. Right. Half of that, it was like, I don't know, like 0.15 or something. Right. For the 2 Newton weight, it was like 0.7 newtons. For the 5 Newton weight, it was like trying to do, scratch that. Right. It was like 1.5 newtons. Right. And maybe the 10 Newton weight was like 3 newtons. Right. I'm just making up numbers, but those might have been realistic. Some of you guys might have found too, if you're dragging this across the desk surface, that wasn't nearly as much friction as, say, if you dragged it across paper. If you dragged it across paper, you probably got a higher value. It's probably easier to read. Some of these numbers were kind of small, so I broke out the blue scales today. Right. Next column, I said, go ahead and take the ratio. I told you exactly what to do right here. I said, go ahead and take the ratio of these two columns. What's this divided by this? Okay. Let's do that all the way down. What is 0.15 divided by 0.5? That's 0.3. What is 0.3 on 1? 0.3. 0.7 on 2. 0.35. 1.5 on 5. 0.3. 3 on 10. 0.3. Okay, what's the average of all those? 0.3, we got 4 of those, plus 0.35, all divided by 5. Okay. The average came out to like 0.31, something like that. Okay. Okay. Now, maybe your ratios don't look exactly as clean as this, because again, I just sort of made this up, but ideally, it should have been pretty similar number all the way down, right? Pretty similar ratio all the way down. Right? What's this graph? Pulling force versus weight. So remember that title tells you what goes on which axis. This is y versus x. So I'm going to put the pulling force in newtons on the vertical axis. Let's put the weight also in newtons on the horizontal axis. Right? So both axes are measured in newtons. Newtons for some kind of force. All right, let's scale these. Looks like my pulling force goes up to 3 newtons, so it'll be 0. Go 1, 2, 3. 0, 1, 2, 3. I should contain my data that way. And my largest weight was 10 newtons. Go 0, 2, 4, 6, 8, 10 newtons. Okay. Let's plot these coordinates. These are like XY coordinates, right? XY coordinates. And so for 0.5 newtons weight, that was 0.15 newtons pulling force. Bam, right there. 1 Newton weight, 0.3 newtons. Bam. 2 Newton weight, it's like 0.7 newtons. Pulling force. Bam. 5 Newton weight was 1.5 newtons pulling force. That'd be 1. So right there, bam, right there. Right. Then 10 newtons was like 3 newtons of pulling force. Bam. Right. Right. And your graph might not look exactly as pretty. That's okay if it doesn't. Right. Right. But ideally, it should those points should pretty well lie on a straight line, showing a direct relationship. Right. You guys get some kind of direct relationship from your own data? Hopefully so. Okay. Got a couple of questions down here. First question, what's the equation of that line? Right? What's the relationship between the pulling force and the weight? Right? Do you guys see, if you're sitting in a math class, that this is just y equals mx? Right? Like if you find the slope, then you can just take that slope, multiply by your independent variable, you get the dependent variable. Take the slope, multiply by the weight, you get the predicted pulling force. Right? The power of equations in physics is that the equations in physics give you predictive power. So suppose you picked some other weight that's not one of these 5, and you said, hey, I want to predict how much force is going to take to pull across a constant velocity. Suppose it's like the same surfaces. You could know it's going to be somewhere on this line. Maybe you can interpolate, maybe you can extrapolate if it's like really big force way out here. Okay, something like that. But all it is, the pulling force, I got it set up for you guys, y equals, say pulling force equals, right? The slope of this line times the weight, right? And the slope of this line is really just this number right here, right? Because I had you take the ratio all the way down, so isn't it just like this is your slope? So I could say 0.31 times the weight, or more generally, you could say coefficient of kinetic friction times the weight. Right, right? You guys get that? Right. Now, other perspective, I showed you this before you guys started getting data, but remember, the weight is equivalent to the normal force, right? So that's an important aspect here, right? Because and your pulling force was equivalent to the friction force. Okay? So if you look at this green box right here, if you just rearrange this green box, you're basically getting the same equation that you guys are writing. Okay? Coefficient of friction times the normal force is equivalent to friction force. Okay? Except instead of friction force, you have the pulling force. Instead of normal force, you have the weight. But you guys see it's the same idea, right? Just those substitutions, same idea. Right. The other question, what does mu represent in that equation? You could say the slope of the line above. You could say the coefficient of kinetic friction. Right? Like both those would be true, right? The slope of this line is the coefficient of kinetic friction, which for me, just the numbers I made up is like about 0.3. Okay. Right, you guys got that? Right. Of course, you guys have your own data, but it should work out pretty close to that, right? You guys got that? All right, let's switch over to second half of the slide. Or no, right. So you guys are getting the last details from that right there. Any questions about that? What's going on? All right. Yeah. So this is mu sub k. If you have here, mu sub k. Oh, here, that's this right here. That's what that is. Right? It's the coefficient of kinetic friction. Okay. So the coefficient of kinetic friction is the ratio of these two forces, friction force compared to normal force. Right? If you rearrange that, just take the normal force, cross multiply it. Isn't friction force equivalent to these two guys multiplied? Mu times the normal force, right? Like that. Right? And then one more step, since the friction force is equivalent to the pulling force and the normal force is equivalent to the weight, you could also say, like for what you guys just did, that the pulling force is going to be the coefficient of kinetic friction times the weight, as long as you have the setup where you're just pulling it horizontally, right? Okay. At a constant velocity. Okay. All right. The second half of the slab, let's see what's up. Because it turns out that even this is like the most fundamental way you can do this slab to determine coefficient of kinetic friction. There's a kind of a fancy way you can determine coefficient of kinetic friction. You can do that, you can figure it out. You can determine what is coefficient of kinetic friction between two surfaces with nothing but a protractor. Nothing but a protractor. Right? How are we going to do that? Right? Oh, okay, well, it has something to do with you're going to lift your desk at some angle and you're going to measure it. So take the protractor, put the node right there, zero out right there, sweep through. What is this angle? Now, right here, this looks like about 26 degrees. It looks like on this paper, about 26 degrees, something like that. Okay. And you're looking for an angle where it slides down at constant velocity. Right? There's actually two slightly different things you can do with this. You can say the angle that it breaks friction and starts sliding, which is somehow related to the static friction, right? Or you can do what's the angle that slides down at constant velocity, which is related to this kinetic friction. And I want you guys to focus on that one today, right? Even though they're like not too different from each other anyway. But yeah, you want to slide down at constant velocity. Because guys, sliding down at constant velocity, would that be an example of equilibrium? Is sliding at constant velocity equilibrium? Yes, it is, because constant velocity is zero acceleration, which means zero net force, right? So equilibrium might be at rest, or it might be sliding at constant velocity, right? So either way, the forces are going to balance out. There are going to be three forces on that lab weight as it's sliding at constant velocity. It's got, of course, its own weight, which is pull it straight down, right? But remember I told you guys introduce a Cartesian system that's rotated. It's aligned with the surface. Right. Right. So you can break that weight into components. You guys see like a right angle right here, nice right triangle. Okay. The other forces on your lab weight. There's a normal force from the surface. You guys know normal means perpendicular. This is perpendicular to the surface, right? And there's also a friction force, right? Which is going to okay. Let's look at how those relate to the weight. Right? So this normal force is going to balance out with the cosine component of the weight. The friction force has to balance out with the sine component of the weight. You guys see that? Right. Now this is all part of a setup where, again, you guys know where this is leading. Somehow you can get coefficient of friction with nothing but this protractor, right? Right. And this is the setup right here. And so I've got a few other posters I want to take you guys through. Right. Remind you guys that the normal force decreases as you increase this angle. Okay, here's the relationship. Okay, normal force is mg cosine theta. But you guys saw that already. You guys saw that right here. This normal force balances out with this component of the weight. That is mg cosine theta. You guys see that? Same thing, right? So I'm just showing you guys visually if you treat theta as a variable, right? What that will look like. Right? I see that normal force shrinking. Ooh, look at that. Okay. Now this is not exactly related, but so I want to show you guys maybe a contrasting idea so you can see something that looks a little bit outside of what we're doing today. Right? Okay, so zero friction incline. Now we're definitely not working with zero friction. That would be like counter to what you guys are doing, right? But what would that look like? Right? Actually, you guys worked with a zero friction incline a few weeks ago. You guys remember those Hot Wheels cars that were zipping down at constant acceleration? They were accelerating, right? It was kind of like free fall gravity, just slowed down, right? That was probably pretty dang close to this. This could model like Hot Wheels car going down. Right? This is very, very close to zero friction situation. In that case, that Hot Wheels car only had two forces on it, a weight and a normal force. The normal force was balancing out the cosine component of the weight. Therefore, the sine component of the weight was acting as the net force. Right? If you kick over to Newton's second law of motion, right? Say, I wonder how much was the acceleration? Because those cars were definitely accelerating a few weeks ago. Okay? Well, the net force is mg sine theta. You guys see how that substitutes in right there? Right? Oh, and what cancels out? The mass of the car, right? Which some of you guys were explicitly running that version of the experiment. You're taping different lab weights to different cars and realizing, hey, it takes like the same time to go the same distance, right? It was all accelerating the same regardless of its mass, right? Here's, I could have asked you guys this is part of the car incline lab we've been, right? Or maybe that would be a different question, right? Is what is the acceleration of the car, right? It ends up just being this expression right here, the gravity field times sine of this angle. That's it, right? Now, again, that's not exactly what you guys are doing today because we definitely have friction, right? But what I'll tie that into another lab you guys did. Okay. Let's go back to sliding at constant velocity. All right, so now we got the block back in equilibrium. This you guys just saw a few posters ago. The block's in equilibrium. All the forces are balanced out. It's just sliding at constant velocity. It's moving, but the forces are balanced out, right? So we got zero acceleration, therefore zero net force, right? Now let's look at just this compared to this. Wouldn't the friction force and the mg sine theta be balancing each other out? Isn't that true? Right? It's balancing each other out. Therefore, you can add this over, and the friction force is equivalent magnitude to mg sine theta. This is equivalent to this. Okay. Now, something else you guys know from the first half of the lab is that normal force is related to this friction force by the coefficient of kinetic friction. Oh, that's where coefficient of kinetic friction is going to come in. Because that's what you guys are trying to find. What is coefficient of kinetic friction? Well, it's the ratio of these two forces. So I've got part of this proof covered up. But the next step would be you're going to take this friction force and replace it. You're going to substitute coefficient of kinetic friction times the normal force. And the normal force, by the way, is related to the weight. Right? And there's some steps that I've got covered up here. You guys can't see the full poster. Where the coefficient of kinetic friction you can get with nothing but a protractor and a calculator, I guess, right? Protractor and a calculator, right? You guys kind of get the premise? Right? So this one's a little bit deeper conceptually. You have to think a little bit deeper. But I'm gonna stop this video right here. Or actually, sorry, one more thing. Okay. Well, let's look at you guys' lab paper right here. Okay. So record different weights. Maybe I'll just copy paste what I had before. I have this many Newton weight, this many Newton weight, this many Newton weight, this many Newton weight, this many Newton weight. I just copy pasted, bam, right I had before. Right. what's the angle that it slides down at constant velocity, right? And then have you guys do a calculation and a graph, right? So here's where I'll go ahead and stop the video, give you guys some time to get some data, and then I'll restart the video later.